Welcome back to the organ printing course. So in the last lecture of this Bioink properties, we have discussed what are the different ideal properties of Bioink for biofabrication. Also, we have discussed the biomaterial properties that influence the Bioink uh, properties for biofabrication. So in this lecture, we'll discuss what is the role of bioink properties on printability and cellular responses. That means here, if you see here, there are two things we are going to discuss, or two important properties that are going to discuss for in terms of bioink properties, like the printing fidelity and cellular responses. So printing fidelity means when you make a structure, right? When you fabricate a tissue structures, so how, like, whether we have fabricated the structure as per the design, or whether the line width and other dimensions are as per the design or not. That means, suppose my intention is to print a line of 200 micron. Now if I can able to make 200 micron line perfectly, then my printing fidelity is very high. That means the structure, when I make a structure, the structure will look very good if the printing fidelity, so then the printing fidelity is very good. But suppose I print a line, but after that it deforms and the line width becomes 300 or 400, the printing fidelity is not good, right? So with that kind of material, I cannot make a very good structures. What I will have, I can make a structure, but structure will start collapsing and it will the structure will start spreading and it will deform. So the printing fidelity would be not very good if with the if that the structure that deforms, that collapse, that cannot retain its shape, right? So all these things, and the bioink, they have a very high influence on the printing fidelity, right? The other thing is the cellular response. So cellular response means when when we incorporate cells within this kind of bioink, how does cell cell behave within this bioink, like the what happened to the viability, whether the cells are viable within this bioink or not, what happened to the cellular proliferation, whether the cells are growing fine within these things or not, cellular function, like the cellular function, cell migration, gene expression of certain tissue specific genes, expression of proteins. So all these things are how the cells behave, how do cells behave when you encapsulate within the bioink. So these two are very different requirement. For printing fidelity, we'll see that. For printing fidelity, the requirement is very different. For cellular responses, for requirements are very different. So it's a challenging thing to actually satisfy both the requirement for bioprinting by selecting a particular specific type of bioinks, because these two are opposing requirement. For printing fidelity, we need the bioink to have certain properties. For cellular responses, the bioink should have certain other properties. So these are very important requirements. We'll see all these things, like the hydrogel properties. Hydrogel properties, they respond very differently to printing fidelity and also to cellular responses. So we'll discuss in the next few slides. We'll discuss each of these in great detail. Now here we'll see all the things in totality. What are the different bioink aspects of bioink that can have influence says on the printing fidelity and cell response, like the hydrogel properties, gelation mechanism and kinetics. This is another very important criteria that has very high influence on the both these properties. Hydrogel network properties, this is also very for the hydrogel, what kind of network structure they have, and that has direct influence on the on the flowability or the rheology of the material, and so accordingly that can have impact on the printing fidelity and cellular responses. Similarly, fabrication time, the duration of fabrication, right? So that is important because we are exposing the cell to non-natural conditions, right, during fabrication. So that can have impact on the both this thing. Again, shear stress, the because we know that in case of extrusion based bioprinting and also in certain in inkjet bioprinting, There can be stress, shear stress generated on the nozzle wall. So that can have high impact in certain cases on the encapsulated cells within the bioink. So that can also, so shear stress can also influence the printing fidelity and cellular responses. Similarly, nozzle gauge, like what is the size of the nozzle, what diameter, what is the diameter of the nozzle. That is another important factor that can have a role, because nozzle gauge directly correspond to the printing fidelity or the resolution of the structure. It directly proportional to the resolution of the structure. So that there also nozzle gauge has an impact. Then again, the viscosity. Sorry, this could be viscosity. So viscosity of the material bioink is another important factor that can have big role in these stored properties. Now we'll discuss each of these points in great detail. The first thing that we'll discuss is the hydrogel properties. That means whether the material, the properties of the hydrogel actually depend on various factors. These are like the physiochemical nature of the hydrogel, right? Like the polymers. Mostly the hydrogels are there, the polymers. So what is the nature of that polymer? Right? What type of polymer it is. So depending upon the type of polymer, the hydrogel properties will vary. Like each one type of hydrogel may have different properties than the other type of hydrogel. So what are the different types of hydrogel polymer, different hydrogel has. So depending upon that, we may try to understand what kind of properties they have depending on the product. Then the concentration of the material. What is the concentration, the material for this hydrogel? Suppose if I increase the concentration, then all other properties, the viscosity of the material, the mechanical property, all these things will improve, right? So by changing the concentration, actually I can change the hydrogel property. Actually, the physical property of the hydrogel, the rheological property of the hydrogel can change upon changing the concentration. So that's why, like suppose I may make a solid material of 1%, 2%, 3% concentration material, right? Then the proper physical, rheological properties of all this will be very different, right? So we need to identify what concentration suits a particular type of biofabrication, a particular bioprinting application. So they can accordingly we can choose the concept. Then again, the density of the material. Like suppose how dense the material or the hydrogel is, depending upon that, it can also impact the rheology or all these things, right? Molecular weight of the bioink is another criteria, that is, or the molecular weight of the hydrogel, because by molecular weight also we can change the rheological property, right? If the molecular, if you use a very high molecular weight and a low molecular weight, then the rheological property of these things will be very different, right? So accordingly, the hydrogel properties will change. Again, the chemical composition. What is the chemical nature of that hydrogel? Or suppose if it's a mixture, what is the chemical composition? So depending upon that also the hydrogel property may vary. The other thing is linear or branched polymer. Either, so we know that either the polymer can be a linear one, or it can be the branched one, and depending upon that, again the hydrogel properties will vary, right? So all these things. So all these have certain aspect on the hydrogel property, right? All this can impact the hydrogel properties. Now, the another thing, important thing is, based on this the printing fidelity or the cellular response again can vary. Like suppose for bioprinting or printing fidelity, we know the stiffer the hydrogel, the higher the printing fidelity. But for cell culture, the softer the hydrogel, better it is for cell culture, because cells thrive in soft, a water-like viscous environment. Right? It's very soft environment. So that's why for cell culture, the requirement is it should be very soft. The material should be very soft. But for printing fidelity, the material should be the stiffer the hydrogel, the better it is for bioprinting. So that's why this, now here, all these have a direct relation to the hydrogel properties, and in a way it can also impact, this can also impact the printing fidelity and cellular responses. Like the, and in case of bioprinting, we have also earlier discussed that we need to solidify the material upon extrusion or upon deposition. Then the gelation is a factor. Gelation is one of the factor by which we can actually control the gelation of the or solidification of the bioink, right? So that's why gelation is attack. And what it does, it prevent collapsing of the structure. That means the structure, it prevents the structure, it retains the structure of the it retains the printed structure. That means it prevent collapsing, right? So that is one thing. So it basically it fix the shape retention or shape fixation is the major factor that gelatin actually helps in that to now gelation. But here gelation time is important, because suppose if the gelation is fast, so that means that it will retain the shape or fix the shape very fast, so it doesn't allow the shape to collapse. Okay, so before even actually the structure started collapsing, it will fix that, it will retain this thing. But if the suppose the duration is very slow, then the structure will get collapsed by the time it actually gel, right? So that time is very important. Time is the key here for gelation. The other thing is what kind of gelation it is. It is a physical gelation, chemical gelation, photo gelation. What type of gelation it is, depending, because all these have their own rate, gelation rate, right? Ionic gelation is very fast, photo is then chemical gelation is slow. So all these things definitely matters. The other thing is the cytocompatible. The gelation, whatever the gelation mechanism we use, that should be cytocompatible in nature, because cannot use any gelation mechanism that is toxic to the thing, because probably that the gelation can work very well with the material, but we have to see whether that just gelation mechanism is toxic to the cells or not. Otherwise, the cell viability will be hampered. So for printing fidelity, we need high gelation rate, right? Rapid gelation is important for printing fidelity. Like printing fidelity, so the printing structure would be very good. Printed structure would be resolution of the shape and size of the structure would be very good if the gelation is very rapid, but it should not be cytotoxic. That is very important. Then and hydrogel or any polymer, we know that they are the micro chains, right? They are the chains that is present within a particular medium, right? Now here the polymer, because they have these chains, so they have this polymer. Okay, so that's why the network of that polymer is very important. If the polymer has what type of network the polymer has, that is very important, because this polymer network, actually the network of the polymer, that can influence or that can impact the physiochemical nature of the hydrogel, right? Because it determines the stiffness and strength of the hydrogel, right? This polymer network, because if the network is very strong, then it can lead to stiffer hydrogel. If it is thing, or if the strength of the hydrogel would be good, and if the network is not weak, then it can lead to weak strength or less stiffness, less stiff hydrogel. Again, the mesh size here, there's another important factor, because the mesh size that of the polymer network, mesh size means in a particular unit area, unit volume, suppose what is the mesh size, how many structure, how many lines and all these things are there, what is the pore volume in that case. So that mesh is very important, because if the mesh size is high or dense, then that influence the diffusion, because if the through a very dense mesh, the diffusion cannot be faster. Okay, so so that mesh size, so the diffusion is good when the mesh is not that dense, right? And then the other thing is the mesh, typically dense mesh may restrict the cell migration, right? So if the suppose if the structure, if the hydrogel is made up of dense mesh, then the cell migrates within the that thing that is restricted. That means the cell, because when the cells migrate, they need porous structure to migrate through the mesh, or otherwise the hot element, they need to degrade that mesh, those lines. Suppose the fibers, suppose they need to degrade that, and then only they can able to migrate. But if the mesh is very dense, so it will restrict the cell migration. Right? The cell migration will be slow. Other thing is also, if the mesh is very dense, because it restricts the cell migration, cell proliferation, so the tissue formation would be restricted in that kind of dense mesh structure. So that's why the network properties of the hydrogel is very important for cellular migration, cellular functions, basically cellular migration, cellular function, tissue formation, all these things. But if the mesh polymer has dense network, then the polymer will be stiffer. The hardware will be stiffer, but for printing so the printing fidelity would be improved, right? So for printing high printing fidelity, we need the denser mesh or the high network properties. But for cellular function or cell viability, we need less dense mesh or network properties of the polymer. So here also, if you can see here, if you see here, two opposing requirements are there. Right? Then other thing, next thing we have, as we have seen, the fabrication time of the construct. Now again, the fabrication time depends on many things. Like the very first thing is, what is the size of your structure, or the volume of the structure, right? How big or how small is the structure? Depending on that, the fabrication time can vary. Again, so the duration of production can vary depending upon the volume of the structure, right? And as I have already mentioned earlier, that when we actually fabricate, we that time we expose the cells to non-optimal conditions, right? Because during printing, the cells are there within the hydrogel, though we provide all necessary conditions like nutrition, oxygen, all these things are taken care of, but still they are in non-optimal conditions. So the if the fabrication time is less, that means if the we you if with a very small time, if you can fabricate the structure, that is good for the cell viability, other thing. But to do that, again, probably we need to increase the print speed. So high print speed again cause high shear stress, because the shear rate is very high. Shear, and as we increase the shear rate, shear stress will also increase. So the less fabrication time actually good for cell viability, good for cellular viability, because the cells are not exposed to very high non-optimal condition. But again, the print speed will increase. And then the other thing is, and with very high print speed, certain cases the printing fidelity can also go down. So that is another challenge we need to encounter. Other thing is more fabrication time. If the fabrication time is more, then so that means we need to employ, for the same volume construct, we need to employ less print speed, right? So if the printing speed is less, it is good for things like that, because the shear stress can be less, generated shear stress can be generated, cells can be viable. But we are exposing them to non-optimal condition for a longer duration. So the fabrication time, we have to also here also we have to weigh both this the advantage and disadvantage, and then we have to take a call on the fabrication time. The generated shear stress, as we have been discussed earlier, for extrusion based bioprinting, it is very true that whenever we are forcing the material or bioink through a very wide nozzle, then what will happen? At the tip of the nozzle, shear stress gets generated, and that shear stress can cause problem, or then shear stress can actually damage the cells, right? That's what. But the generated shear stress, it depends on many things. One thing is, of course, depending on the shear rate. If the shear rate is high, the generated shear stress will be high. Again, if the viscosity of the material is high, then also the shear stress would be high, because for to extrude high viscous material we need to employ higher force, and accordingly the shear stress can be more, right? So it depends on the other thing is the nozzle size. Now depending upon the nozzle size, suppose I use a 100 micron nozzle and 200 micron nozzle, then definitely in 200 micron nozzle the shear stress would be lesser than 100 micron nozzle, because depending on the nozzle size also, with the as we go low, as the nozzle size goes lower, then the shear stress will be more. Again, nozzle geometry. It has been seen that when we use tapered nozzle, like this nozzle, when the nozzle is tapered, right? At the tip, the diameter is less, but at the when it is connected to the ceiling, there the diameter is more. In case of tapered nozzle, the shear stress is mostly generated at the tip of the nozzle, right? But when the nozzle is straight, in straight nozzle, the shear stress can generate at the throughout the inner wall of the nozzle. So that's why the tapered nozzle is so better than the straight nozzle for bioprinting. So the nozzle geometry also has a key role on the generated shear stress. And as I already mentioned, then with extrusion rate, the shear stress also increases. The viscosity also play a big role here. With increasing viscosity also, the shear stress increases. And high shear stress is very bad for the cells, so that can cause cell damage. So we need to take care of the process, choosing the bioink, choosing the right viscosity, with the right gelation, all these things, so that the less shear stress generated, and that can the cells will be viable. Other than this, the nozzle gas, as I have already mentioned, for printing fidelity, we need low nozzle size, low diameter nozzle, right? Because it influences the resolution. If my printing nozzle is very fine, diameter is very fine, then I can make a very nice structures. I can make very small, and I can make a very good structure. So the resolution of the structure can be influenced by the or directly influenced by the nozzle gas. Again, it also influences the fabrication speed, because if I use a lower size nozzle, then the fabrication speed will decrease. Okay, right? Because I am putting very less material and I am trying to make a big structure. So the nozzle gas actually influence the fabrication speed, but also in terms of cellular viability, again here you have to see that with higher nozzle gauge there is a less stress generation, right? So that's why with higher nozzle gauge the cellular viability will improve, but the resolution will be compromised, printing fidelity can also be compromised, right? So the nozzle gauge that also high influence on cell viability, and accordingly we have to choose a nozzle gauge where both the printing fidelity and also the cell viability is good. Viscosity, as we have already discussed, viscosity is the resistance to flow, right? When we apply, suppose when we apply force on the material, if it resists to flow, that is viscosity, right? And viscosity, how viscosity influences the printing fidelity and the viability, because if the material is high viscous, then it retards the collapse of the structure. Because if I print a structure, suppose I print a structure with high viscous material, then the printed structure will be collapsed, but that rate of collapsing would be low, because the viscosity actually that holds the material together, right? So because it prevents the flow, so it holds the material together, so that it retards the collapse of the structure. But it also determines the shear stress. Okay, if the viscosity is high, the shear stress also will be high for extrusion. High viscosity definitely improves the printability. When the viscosity of the material is very high, then the printability of the material improves, right? And also when the viscosity is high, that may influence cell viability. That means and it has been seen that it has been proven that when the cells are embedded in a high viscous material, their viability also reduced and the functionality also reduced, because the cells are, that is they are cells find difficulty in migrating within the viscous material. That's why for printing fidelity here, the important thing is for printing fidelity, high viscous material is good. For cellular cell culture, low viscous material is good. So we have to, again, here also we have to compromise, or we have to adjust between these two properties. So after going through all these things, now we can discuss, as we have clearly seen that for fabrication of complex tissue-like structures with high resolution, where the printing fidelity is very good, when you can make a very good structure, for that stiffer hydrogel is required. And stiffer hydrogel means that can be high viscosity, high network properties, high concentration, all these things, right? But for cell migration, proliferation, and differentiation, softer hydrogel is required, because the cells, they thrive in soft that environment. They can grow well, they can do all this function well. So these two poses two different challenges for selecting bioink, right? But suppose for printing fidelity, you need a stiffer hydrogel. For cell culture, you need a softer hydrogel, right? So accordingly, if you see, there we can discuss that there is a biofabrication window where actually we can work basically. Beyond this, suppose if we go very stiff environment, then that is not good for cells. If we go very low environment, very low in micro environment with softer hydrogel, then that is not very good for printing fidelity, right? So accordingly, we are there somewhere in between these two zones, where we are compromising to certain extent the printing fidelity and also the cell viability, to select some area in the whole range that we can call as a biofabrication window. So typically for fabrication, any fabrication, high ship fidelity is important. When, of course, when there is no cells involved, then high ship fidelity is possible. So the typically for fabrication, high ship fidelity or printing fidelity is very typically high, right? But for cell culture, with the cells need a very water-like environment. But with water-like environment, the ship fidelity is very low. The printing fidelity will be very low. We cannot make a 3D structure with water-like viscous material. So ship fidelity will be very low. Now that's why traditional biofabrication approaches, where we use less viscous bioink, so that leads to low ship fidelity but good cell viability, right? So traditional biofabrication is in between these two, where we are not using very high viscous bioink, we are not using very low viscous bioink. So that's why we are using moderate viscous bioink, and shape fidelity is okay, low shape fidelity, but that is the cell viability is good. But we need some novel biofabrication approach where the shape fidelity can be improved further without compromising the cell viability. That means we have to, the novel biofabrication method is required, where that the shape fidelity improves but the cell viability without compromising the cell viability, right? So we are, so for fabrication we are almost where high shape fidelity, high viscous bioink can be used. For traditional biofabrication, we are somewhere in the middle, where modern viscous bioink is used, and we go with good cell viability. But novel fabrication, again, we can push this towards this thing where we can use very high viscous bioink, or separately can be very good, but the cell viability would be also good, because in case of fabrication, we know that if we increase the mechanical properties of the thing, the viscosity of the rheological property or viscosity of the bioink improve, then the printing fidelity can be improved, but that can also lead to low cell viability. So the important thing to remember here is we need to come up with a novel fabrication techniques where the printing fidelity would be very good without compromising the cell viability. And to do that, we need to understand the rheological properties of the materials. And as we have earlier discussed also, The rheology is nothing but the study of the flow of matter upon application of an external force, right? So where we apply force on the material withstand the force and the material will start flowing, right? But when it resists it can either it can resist to certain forces. So that all these things, we'll discuss in this one by one, right? But it has very high relevance to biofabrication, because rheology, you have to study the rheology in great detail when you actually going for actually bioprinting, where this has typically we need to understand this thing. And the flow of the material through a nozzle, that is relevant for inkjet and extrusion bioprinting. So that's why this is very relevant, because in this case, in case of inkjet and extrusion bioprinting, we are in our this thing. The process is such that we need the material should be flowing through the nozzle. So in that case, inkjet bioprinting, it should come out in the form of droplets, but in case of extrusion, it comes out in the form of filament. But in any case, anyway, in any of these two, the material should be able to flow through the nozzle. And all these rheology properties are very important, like the viscosity of the material is an important rheological property that we need to understand. Shear thinning behavior of the material, that is another important rheological behavior we need to understand in great detail. And the yield stress has typically some very important aspect, is a very important aspect for rheology, the rheological properties that we need to understand for biopainting. Now we'll discuss each of these rheological properties with certain degree of clarification. Like, let's first start with viscosity. The viscosity, as we mentioned earlier, it is the resistance of a fluid to flow upon application of applied shear stress, right? So when you apply shear stress on a material, or when you apply force on the material, then the material will prevent the first, it will prevent the race, it resists the flow. But after some time, a certain time, it should start flowing. So that is the viscosity. So that is the resistance, that is the viscosity. High viscosity, basically if the material is very high viscous, whenever it's actually in case of bioprinting or any fabrication, if when we are working with these hydrogel materials or any type of this kind of polymer solution, what will happen? There will be two opposing factors, like opposing forces, viscosity and the surface tension. Surface tension, it will lead the material to form a droplet. But the surface, if the material has high surface tension, that impedes the surface tension driven droplet formation. That means it prevents the droplet formation. It actually helps the structure to remain in that printed form, right? But high viscosity also impedes the collapse of the deposited structure, because if I print the structure with a very high viscous material, the very high viscous material, then what will happen? It prevents the collapsing of that structure, because the viscosity that will hold the material together, and it will prevent the collapsing of the structure. So the viscosity, it impedes both surface tension driven droplet formation and also collapsing of the deposited structures. Other important thing about the viscosity is the viscosity directly influences the shape fidelity after deposition. That means after extrusion of the material through the nozzle, the viscosity that holds up the structure, right? So the viscosity, one thing is it prevents collapsing, it retards deformation of the structure, so it improves the shape fidelity after deposition, and then some kind of cross-linking can be utilized to further arrest the flow of the material or to retain the shape of the structure. Here, high polymer concentration can be a restricted environment for polymer cell proliferation, migration, and tissue formation. Like many times, what we do to improve the viscosity, we increase the polymer concentration within the bioink, right? And also, but that high polymer concentration, that can be a restricted environment for the cells to function, to migrate, right? And the other thing is applied shear stress also increases with increasing viscosity. Suppose if we are increasing the viscosity, then what will happen? Again, the shear stress can be more. So the more shear stress can be generated when we are trying to increase the viscosity. So that is another factor that we need to load we need to understand or study. But one thing was seen before, like when it has been observed that the cells can survive, or cells are very much resilient to an exposure of very high shear stress for a very less time. Suppose I apply high shear stress to the encapsulated cells for a very minimum time, then that the cells can able to withstand that for a very less time. So that is actually good for bioprinting, because in bioprinting also the cells actually they experience high shear stress, but that is for a very less time. Right? But it has been found that very high shear stress for a very transient time, less time, it doesn't reduce the viscosity. Sorry, it doesn't reduce the cell viability. So that is actually good for our thing. The other thing is, as we have discussed earlier also, the shear thinning is a behavior that is very good for bioprinting, because it's an actually shear thinning is a non-Newtonian behavior in which the viscosity decreases as the shear rate increases. So with increasing shear rate, the viscosity decreases. And as you know, in our extrusion-based bioprinting, especially when we extrude the material forcing material experience pressure or shear force, and because of the shear stress generated shear stress, then that can cause damage. The high viscosity, because of this thing, the printing fidelity can be also good, because shear induced shear force, what it does actually, why some materials they behave like a shear thinning material, because the material has typically the material has certain organization of the polymer chains, right? The polymer chains are organized in certain way. Now because of that, they behave like a very tough, or they behave like a solid materials, or sorry, they behave like a stiff material at the beginning. The viscosity will be very high because they resist the flow, right? But when we apply shear force, that shear actually reorganize the network structure within the polymer chains. Okay, so ultimately, when the polymer, suppose in the resting stage, suppose some kind of network is there within the polymer chain, but when you apply shear force, that shear actually reorganize the polymer chains to a more stretched conformation, so that there's a less entanglement, and they can easily come out of the nozzle. So that basically that helps, that's just induce reorganization that helps the material to come out. So that means with increasing shear rate, here the viscosity of the material comes down because of this reorganization. Right? That's why most polymer system they actually experience this kind of thing, shear thinning behavior. Okay. The other than this is, whenever I withstand the, suppose I withstand the shear, we withstand the shear force, again the viscosity will be increased further. Again, the reorganization will start happening. That means this material can come back to the again the thing. So shear thinning is very important for bioprinting, because with shear thinning, actually we can easily extrude the material out of the nozzle. Most polymers that they display the shear thinning behavior, and the polymers with high molecular weight exhibit prominent shear thinning behavior, because in case of high concentrated material, high molecular weight polymer material, because the chain length is longer, so in that case, the entanglement can be also very high, right? Chances of entanglement will be high. So if when I apply shear rate, that shear rate helps them in this, because that put them in the stretch conformation, right? So that can easily come out. After that, again they come back to the original shape and this thing. So polymer with high molecular, they exhibit prominent shear thinning behavior can be seen with polymer with higher molecular weight. Again, for higher concentration, the relative reduction in viscosity induced by shear rate is even greater. Like if the molecule concentration is higher in the polymer in a bioink, then what will happen? The reduction in viscosity upon applying shear, that is a very even greater. So we can actually that experience that thing. We can actually study that how much amount of shear rate reduces because of this high shear rate. Viscosity reduces. Another thing is decreased viscosity at the high shear rate during biofabrication, followed by a sharp increase in viscosity upon deposition, resulting in high printing fidelity. Here, the important thing is As earlier also we have mentioned that the viscosity, basically higher viscosity, that prevents the collapsing of structures. It retards the deformation, collapsing of the structure. That means if the material at the beginning, the material behaves like a very high viscous material, or the gelatin, the viscosity is high, and again when you push them due to reorganization, the viscosity comes down, so that time it is easy to come out of the nozzle. Again when the shear is, so they are outside the nozzle, then the pressure, there is no shear force applied on this on them, so again the viscosity will increase further. So it helps in the printing fidelity. So the printing fidelity could be much higher in case of the shear thinning material. Yield stress is another critical important thing to understand, because yield stress is the critical stage that must be overcome to initiate flow. That means all hydrogel, because of this networking properties, most of the hydrogel they possess shear yield stress. That means when you apply shear rate or apply force, the material will not be flowing until the force reaches beyond a critical value. That means that we have to overcome that critical state, then only the flow can be initiated. That is yield stress, right? And yield stress basically it forms because of the polymer chains. What happens, they form a fragile physically cross-linked network. Most of the polymers they form this thing, physically cross-linked network, but it is a fragile one. So that can be broken down by applying shear force. So when you apply shear force, that physical cross-linking network can be broken down. So that is above, that is the yield stress. At the yield stress actually we can basically break down that network, crossing network, physical crossing network, and the material start flowing. Again, when if shear is removed, if the force is removed from there, then the broken physical crossing reworks again, then reforms. The reformation of the broken physical network happen whenever there is the thing. That's why it can be used. The other thing is yield stress potentially prevents flow and collapse. So now suppose when the material has a typically yield stress, that will prevent the material from flow and collapsing of the structure. So yield stress, having yield stress is good for bioprinting, for this kind of bioinks, because it prevents the flow of the material, and the collapsing of the material also can be preventing by yield stress. Other thing, yield stress prevents cell settling in the hydrogel precursor solution, because if the material has yield stress, so typically it has physically cross-linked structures, so it holds the cells also together at their respective places, so the cells will not settle down. That can happen with low viscous material, typically that can happen. But if that material also have say certain yield stress, so definitely it will prevent the cell settling. So the cellular distribution, or the cell can be homogeneously distributed. They will not settle at the bottom of the hydrogel precursor solution. So these all things are very important to understand. These properties, the rheological properties like the viscosity, shear thinning, and yield stress. These actually very important properties that helps in bioprinting. But all these actually that helps in printing fidelity. The printing fidelity goes good if the material is highly viscous, if it has a high yield stress, and it is a prominent shear thinning behavior.